function in the sense that it is smooth, means that we can talk about dou alpha by dou x power alpha of f with respect to x, okay, are all defined. Exists in the moment I talk about higher derivatives, means that the previous derivatives exist in a neighborhood of f. Okay, so that is the meaning of the smooth. So we can actually have a sequence like this. So once we have a sequence like this, then we'll see how the once if you have the sequence, then f epsilon from these conditions, you see that f epsilon, because this is now exists and things like that. So therefore, if it exists in a neighborhood, you have it to be bounded also. Therefore, since dou f by dou x is bounded, these f epsilon are going to be ellipsis functions. Then one considers the x epsilon prime equals to f epsilon of t x epsilon. Problem like this, okay, and these problems will have a solution because if epsilon is local ellipsis, is going to be ellipsis. Therefore, okay, by Picard's theorem, you have a solution. There exists x epsilon. Now look at the x epsilon. X epsilon satisfies two equations. One is that x epsilon prime is f epsilon of t comma x epsilon. This is one, and also x epsilon satisfies the integral equation because it's a solution. Okay, because it's a solution. Satisfies x naught plus the integral t naught to t. So from these two equations, you see that this implies mod of x epsilon prime, okay, is less than or equals to m. Okay, and also this implies that mod x epsilon is less than or equals to mod x naught plus this is m into h. So from here you see that this epsilon prime is bounded and this is also bounded. Therefore, this implies x epsilon is compact. Okay, it's a compact subset, okay, of C. So this implies that x epsilon has a convergent subsequence, right? So if x epsilon is a convergent subsequence, say let me call x epsilon itself, okay, you can call it epsilon k also, something if you want, converges to x uniform, and apply this in integral equation here, you get the solution x to be a solution. So what the idea here is that you approximate these nonlinearities by smooth functions. So that approximation by smooth functions here, how such a thing can be obtained, f epsilon. So I gave a couple of problems in the tutorial sheet. So I'll tell you what these functions are.
Hello sir.
Yes.
सर आपने कहा कि f is continuous but not ellipsis. सर ये एप्सिलॉन जो है ना, f एप्सिलॉन बिना सीक्वेंस, तो ये सर एग्जिस्ट कर रही है, तो मतलब कैसे कर रही है, मतलब कोई आइडिया?
That's what I am giving you now, right? Existence of f epsilon. How to define such f epsilons. Okay, so this is these are called. You take a function which is defined like this: exponential of -1 by 1 minus x square, and it is 0. So this is true for x in, you can see that x square is 1 minus x square less than or equals to 1, therefore from -1 to 1, otherwise it is going to be 0. So this function is a smooth function. This is f is going to be C infinity function, and f is going to be 0 in, it is defined, f is 0 in r minus -1 to 1. Okay, and moreover, this is a smooth function. It is differentiable at 1 and -1. These things you can check. Okay, so you define now a sequence rho epsilon. Okay, so rho epsilon of x equals to 1 by epsilon into f of x by epsilon. Okay, so you also multiply by a constant here. Okay, so you multiply by a constant here, and C is such that the integral of f is 1. Okay, so you write the integral of this, and then there will be a constant. So choose the constant so that this integral is 1. Then these integrals are all going to be 1. Then these f epsilons are produced okay, like this. F epsilons are produced like this. So you write this rho epsilon. This is called convolution with respect to x. Okay, so this is defined like this: the integral over r of rho epsilon x minus y f y dy. Okay, so one can show that these f of t comma y, these are f of t comma y. So you can show that these functions are differentiable. So this is left to you as an exercise. So your tutorial teacher will prove this to you. So differentiable means you just write the first principle, the definition: limit h goes to 0 of f epsilon of t x plus h minus f of t x by h. So these functions are differentiable, as many times as you wish. Therefore, since they are differentiable, you know that if you have the dou f by dou y is bounded, okay, implies f is Lipschitz. Because of that, the f epsilon. So this, since things are bounded, therefore f epsilon are going to be this Lipschitz functions. Moreover, you can show that this f epsilons, okay, are going to converge uniformly to f. So these uniform convergence, these things you can easily prove by the simple methods. They are not at all difficult. The formula is given to you here. Just estimate f epsilon minus f, write the supremum of this, and then you can do that. You can show that this goes to 0. Okay. So this is the way. These are some of the new proofs which are given for the Peano's theorem using some of the latest techniques that are available in the mathematical analysis. Of course, you will find many other proofs. Okay. So the whole idea is to, whatever the thing which is not smooth in an equation, okay, whatever is that which is not smooth in an equation, approximate this, perturb this by smooth functions, and then produce a solution, and then see that these solutions converge in appropriate topology or appropriate norm or an appropriate way, so that we can pass through the limit in the final equation. So this is the whole idea. Okay, so this is also called, that is why it is called the approximation technique, or it is also called the regularization technique. What we are doing is we are regularizing this f by f epsilon. Okay, so these are some of the things. Then there are some solutions which are important. These are called, yes.
सर इसमें सर f को सर बाउंड्री लिया गया है पहले से ही, assume किया गया है.
Yes, of course, f is a continuous function, therefore f is going to be bounded in the rectangle, right?
Okay.
So everything we are doing within the rectangle. All these things we are doing within the rectangle, for the local existence only.
And sir, also sir जो आपने लिखा है x epsilon is compact subset of C, सर इसका मतलब क्या है?
Compact subset, I said, right, in the Ascoli-Wurzel theorem. That means it has a subsequence which converges.
Yes, in that subset also. Okay.
That's what we say in the Bolzano-Weierstrass theorem, right? A sequence is compact.
Yes.
Means it has a convergent subsequence. Because that's what I said in the previous lecture, Ascoli-Wurzel theorem.
Yes, sir.
So singular solutions, what are these singular? These are the very special solutions or special ones which are not found by solving the equation by some of the methods. Okay. So the methods does not give any these solutions. So what are these solutions? These solutions are the ones which are coming as envelopes of one parameter family of solutions. Say for example, what are these envelopes? I'll tell you through an example, then you can remember what these envelopes look like rather than giving a mathematical definition. So look at the equation what I gave earlier, the square root of y. You can write square root of mod y, doesn't matter. Once if you write the solutions, you will write what is the square root of y, because it's meaningful only for those solutions. So if I take this, then you have the solutions like this. So you have the solutions x square you can write, okay, or you can take it to be 0, or you can write them to be like this. All these functions, all these ones, they are actually passing through this point, are actually touching this y equals to 0. Okay, see that they are all touching y equals to 0, and from each point of y equals to 0, you have one solution. From each point of y equals to 0, you have one solution. So why it is happening? That is actually at each point of y, you have one solution which is passing through this. That is, there are two functions where the values of the function is the same at this point, and also the slopes are the same. Also, the slopes are the same. That is what we require here. In the equation, first order equations, it's a very special phenomena only for the first order equations. In the first order equations, you look at the only y prime, that is the slope, and the function. And on this curve y equals to 0, it is so happening that at every point of this, there is one function which is a solution which is passing through this, which is touching this. That means both of them have a common point at this point, at one point, and at that point the slopes are also same. That means the equation is satisfied. Therefore, we are able to see that y equals to 0 is the solution. So this y equals to 0 is called envelope. It's called envelope. How does one obtain this envelope? Is for a family of curves. So I call it as phi tc is a family. Family of curves. Okay. Then you write the phi tc. You can write xtc or x phi equals to 0, and dou phi by dou c, which is equals to 0. So differentiate them with respect to the constant c. Okay, solve these two equations. That is called, that gives the solution of this. Is the envelope. Okay. So let us. So you can see here that what is the solution here. In this case, we found y equals to x minus c square by 4, right? Is what we found. So if you write dou y by dou c, Okay, so this becomes 2 into x minus c. Of course, there will be minus 1. So if I make this to be 0, this implies that x equals to c. So if I put this x equals to c in the equation, this put it here, this implies y equals to 0. So this is the envelope. This is the envelope. So it's what here we are seeing is that if you are given one parameter family of curves, then you can find envelope. Okay, so at times it may not be easy to find this one parameter family. If you can find one parameter family, it's fine. We can write these two equations, and then, for example, y prime equals to square root of 1 minus y square. So you can see that the solution of this, the constant is sin t plus. Okay, so we can write from minus pi by 2 locally, and so this is the solution, and you see that how the solutions look like. So minus pi by 2 and pi by 2. So this is sin 0 is 0. It's look like this. Okay, and these curves which are translated, okay, so like this. Translated this. So you see that all these curves has y equals to plus minus c. That is how these curves touch these points on y equals to plus minus. Geometrically, that's what we see. And therefore, that's what we also will find cos t plus c to differentiate this dou phi by dou c equals to 0 implies c equals to plus minus pi by 2. Okay, so that gives y equals to plus minus 1. So these are the two lines which are actually coming as envelopes of this one parameter family. Okay. So similarly, I gave other examples. You can see those. So what is important I wanted to tell you here is that at times it may not be easy to find the envelope, that is the one parameter family. Okay. So in that case, let's see how this one parameter family or the envelope equations are equivalent to, at least in some cases. Say, for example, if I am given the equation to be in the form of x prime equals to 0. Okay, and you have then you differentiate this. Okay, when I differentiate this, or assume that let phi be a solution, x equals to phi tc be solution. Then we have f of t phi, okay, and phi t equals to 0. Now differentiate this with respect to c. When we differentiate this with respect to c, by chain rule in multivariable calculus, I get this to be fx times this thing, and this is differentiated with respect to c, plus f x prime into the phi t is differentiated with respect to c. Okay, so this is equals to 0. So from here, if phi c is 0, as in the envelope, right? As in the envelope equation, if phi c is 0, the first term is already 0. Okay. Then f x prime is 0. On the other hand, we also have that if fx is not identically 0 and fx prime is 0, then phi c has to be 0. You see that phi c equals to 0 implies fx prime is 0 and fx prime equals to 0 implies phi c is 0, but you have a condition that fx is not 0. So if fx is non-zero, then phi c equals to 0 and fx prime equals to 0 are equivalent. So the envelope actually can be found by writing fx prime equals to 0 and fx not equals to 0. So the envelope equation, we need not actually find what is the one parameter family. Okay, we can solve f equals to 0, fx not equals to 0 and fx prime is 0. That also satisfies the envelope. So let's see how this works for some examples. So let us take function f, which is equals to 1 plus y prime square minus 1 by y square. So the equation is, the problem is, the equation is 1 plus y prime square equals to 1 by y square. So this is the equation, and therefore f is this. So if I write what is dou f by dou y prime, okay, it is simply 2 times y prime. So you can also write f to be any other way, that is you can also write f equals to y square into 1 plus y prime square. I think this is what I wrote in the equation, so that we also will get the same thing. So even if you take this one, this dou f by dou y prime is going to be y square into 2y prime. Okay, so this is equals to 0, right? So this implies you don't take y equals to 0, doesn't satisfy this equation. Therefore, we take y prime equals to 0. Okay, so put y prime equals to 0 in the this equation. Therefore, minus 1. So put this y prime equals to 0 in this equation. This implies, okay, f equals to 0. This implies y equals to 1. Y equals to minus 1. Right. So these are the envelopes that we are getting. So also we can solve this equation. So solving this equation by separation of variables. So the solution is given in the notes. You can see. I'm not going to solve this by separation of variables, but the solution is given to you. So we get y square plus t plus c whole square equals to 1. So you can see what these curves are. Okay, these curves are such a way that y is just center is on the c, the constant c, right on the x-axis. So they are all looking like this. So you can see that y equals to plus minus 1 are the envelopes. Okay, y equals to plus minus 1 are the envelopes. There is one more equation which I wanted to give here. Say take y prime square into 1 minus y whole square equals to 2 minus y. So when you differentiate this with respect to y prime, that is y prime, we have the right 2 into y prime, right, into 1 minus y whole square. 0. So this implies that y equals to 1 or y prime equals to 0. Okay, Now you write d dou f by dou y. So if I write dou f by dou y, I have y prime square into 1 minus y is equals to minus 1, right? No, don't do this. Yeah. So you get this, and you write. You can write the general solution. So from the general solution, you will see that you have the y plus 1 square into 2 minus y equals to 0. Okay. So this also gives the y equals to 2 is the envelope. And if you see this equation, y equals to 1 is not a solution. This is not a solution. Therefore, y prime equals to 0. When we put y prime equals to 0, you get the left hand side is 0, therefore y equals to 2. So y prime equals to 0 implies y equals to 2 is a solution. So this is the way to find the singular solutions. And so there also I gave one more equation, which is a class of equations which is known as the Claret's equation. So these are some things about the singular solutions which are not actually found by methods that we use for, or these are not actually part of the general solutions. They are not part of the one parameter family of general solutions. Do you have any questions?